A binomial indicating the subtraction of two perfect squares is called a difference of squares. A difference of squares results from multiplying binomials containing the sum and difference of the same two terms. As we can see from the pattern, the quantity a plus b times the quantity a minus b yields the difference of squares binomial a squared minus b squared. Note that in a difference of squares, the terms of the binomial must both be perfect squares, and the terms must have different signs. These facts help us to identify difference of squares binomials, which are a polynomial that's relatively easy to factor. So in order to factor a difference of squares binomial correctly, we must be able to recognize this type of polynomial. Let's look at some examples and determine whether or not each of the following is a difference of squares. The first example is 9x squared minus 64. Does this fit the pattern of a difference of squares? Well, we look at the first term, we can see that it's a perfect square. 9x squared is actually the square of the monomial 3x. In the second term, 64 is a perfect square as well. It's 8 squared. And we see the minus sign between the two terms. So yes, we do have a difference of squares binomial in which a equals 3x and b equals 8. So it fits the pattern of a squared minus b squared. What about the second example, x to the 8th plus 25? Well, we can see that x to the 8th is also a perfect square. It's the square of x to the 4th, and 25 is a perfect square as well. However, we see the plus sign between the two terms. Both terms are positive. Since the terms have the same sign, this is not a difference of squares binomial. It's actually a sum of squares, and a sum of squares is a type of polynomial that cannot be factored. Next, we have 36 minus n to the 5th. In this case, the first term, 36, is definitely a perfect square, and we see the minus sign. However, n to the 5th, since we have an odd exponent on our variable, that term is not a perfect square. So this binomial is not a difference of squares because of that odd exponent. And finally, negative a squared plus 81. In this case, both terms have different signs, and a squared and 81 are both perfect squares. So yes, this is a difference of squares binomial. It might be a little bit easier to identify as a difference of squares if we first rewrite it according to the commutative property as 81 minus a squared. And then we can clearly see that once we've used the commutative property, it does fit the pattern. Now let's go through some examples of factoring difference of squares polynomials. Our first problem is 49x squared minus 4. We can see that it definitely does fit the difference of squares pattern. In this case, a squared is 49x squared, so a is 7x. And b squared is 4, so b is 2. This means we can factor this as the product of the binomials 7x plus 2 and 7x minus 2. What about example 2? We have x to the 5th minus 9x cubed. Because of the odd exponents, this binomial is actually not a difference of squares. However, we can first begin the factoring process by using the distributive property to factor out the common factor of x cubed. And the remaining binomial we have in the parentheses is x squared minus 9. And that binomial is a difference of squares. So our final result is x cubed times the quantity x plus 3 times the quantity x minus 3. Problem 3, we have negative 32 plus 50n squared. Might be a little bit easier to look at this polynomial if it's written in descending order. So let's rewrite it using the commutative property as 50n squared minus 32. Once again, this is not a difference of squares. We don't have perfect squares for those two terms, but there is a greatest common factor that can be removed. In this case, 50 and 32 are both divisible by 2. And then the binomial we have in the parentheses would be 25n squared minus 16. And that is a difference of squares, so we can continue factoring and write the answer as 2 times the quantity 5n plus 4 times the quantity 5n minus 4. And our final example, x to the fourth minus 16y to the fourth. This is a difference of squares. The square root of x to the fourth is x squared, and the square root of 16y to the fourth is 4y squared. So we have x squared plus 4y squared times the quantity x squared minus 4y squared. Now we always want to make sure we factor a polynomial completely. Notice that the first of those two binomials we've written is a sum of squares and cannot be factored, but the second binomial is another difference of squares. So in our final answer, we have our original sum of squares, and then the difference of squares factors into two more binomials, the quantity x plus 2y times the quantity x minus 2y.